Welcome everyone for this afternoon session. We will have the topic development of toolpath and integrated workflow with the parametric modeling approach in robotic wire arc additive manufacturing method with Enes Aslan. So please welcome Mr. Aslan for his presentation. Thank you.
Ekranı yansıtıyor musun?
Evet.
Şuraya yansıtabiliyor muyum acaba? Gözüküyor mu? Thank you. Dear professors, welcome to my presentation. My name is Enes Aslan. I am a research assistant. I'm a research assistant at Ankara Yıldırım Beyazıt University, and also I am doing my master degree under the supervision of Professor Dr. Oğuzhan Yılmaz at Gazi University. And I will present our study. First of all, I want to start explain the one process. One process, so wire arc additive manufacturing is one of the metal additive manufacturing techniques that utilizes wire as the raw material and the performance production using the arc energy. Compared to another metal additive manufacturing techniques, WAM offers the advantages such as low cost and high material efficiency and high deposition rate. And WAM, in particular, enables the production of the large-scale and complex components. This is one of the primary reasons for the increasing preference for WAM in the recent years. And the another page, yes. And then metal additive manufacturing methods generally consist of the, yes. Okay, thank you. Metal additive manufacturing methods generally consist of the 6 basic stages as shown in the figure 1. These stages are 3D part design, slicing, tool path development, produce simulation, and conversion of the created tool paths into the machine language, and finally production or deposition. You can see some software developed for this process in the figure 2. However, this software available on the market generally offer solutions only for one or a few stage. So using different software for the production stage in the one process can cause many errors and decrease workflow efficiency and increase the production times. Therefore, there is a need for a workflow and that integrates all these steps into the only single the software platform. In this study, we developed the parametric workflow that integrates all stages of the robotic arm process into the single software. We choose the Grasshopper software as the platform on which the workflow will be created. Grasshopper, what is Grasshopper? Grasshopper is a visual programming tool with parametric modeling and algorithm development capabilities. And thanks to parametric modeling, changes made in the created model can be displayed instantly. Thus, flexibility is provided throughout the process, and users can instantly control every step of the model. Our workflow covers the entire process from 3D modeling to slicing and toolpath generation and robot programming. As the first stage of the one process, we parametrically designed the 3D CAD model of the part to be produced in Grasshopper. You can see the design part in the figure 3. Each part of the workpiece has on an octagonal cross-section, and it bent is and is bent at a 13 degrees angle at the different heights. The parametric structure developed for the part design is the figure illustrated in the figure 4. Subsequent to parametric model creation, a slicing strategy was developed as an alternative to existing slicing software. A strategy grounded in the direct slicing of the NURBS model within Grasshopper was devised. This strategy enhanced both the dimensional accuracy of the part resulting from the production deposition process and the performance of the robotic production. And figure 5 presents the algorithm developed for the slicing method strategy. And toolpath planning is the one of the most critical important stage in the one process. Contour pattern was selected as the path pattern in this study. Contour pattern is commonly used in the one method. In the one process, sorry about that. In the one process, the geometry of the weld seam is generally as shown in the figure 6. As you can see, the weld seam has the profile with a height difference between the start and end points. To solve this problem, we shift the deposition starting points in each layer so that they would not align. In this way, we aim to create a much more homogeneous deposition. Figure 7 presents the algorithm and developed for the parametric toolpath planning in this study. Moreover, you can see same time the front and top view of the developed toolpath in the figure 8. And after creating the toolpath, as shown the figure in figure 9, we developed an algorithm to simulate the deposition process. Thanks to this algorithm, we were able to visually follow the production process according to different deposition ratio and detect any errors in advance. As seen in figure 10, the simulation results clearly demonstrate the progress of the deposition process at different stages. And you can see the simulation of the deposition in this video. And then the program, the industrial robots, we use the KUKA PRC plugin developed for the Grasshopper as a post-processor. This plugin enables the conversion of the parametrically generate toolpaths into the robot commands and the period the simulation of the robot's movements during the production. In this study, and we used the KUKA KR16 ARC robot and was selected as the industrial robot arm. And the necessary parameters for the deposition parameters you presented in the table 1. A flowchart illustrates the entirety of the workflow developed in this study. The process encompasses all steps from chat model, modeling to slicing, toolpath generation, simulation, and robotic production. Finally, as conclusion, in this study, all phases of the one process were executed using the algorithm developed in the Grasshopper. Only one single software we used. As the algorithm developed in this process have a parametric structure, they can be really adapted workpiece with different geometries. Additionally, parameters such as layer height, bed width, overlap amount, and torch fit rate, and can be easily customized for each part in the Grasshopper by developing the process within a single software. So that data transfer errors and process delays resulting from the use of multiple software program are eliminated and significantly enhancing efficiency. These factors have made the one process more flexible and efficient. And future works. In the study, we used a 2.5D slicing strategy. Thus, future studies plan to develop the workflow for more complex parts and with overhanging geometries. Moreover, monitoring the deposition parameters in the one process using the automatic feedback systems will be the focus of our next and future research. And with this study, we believe that we have taken the significant steps to make robotic one process more efficient. Thanks for your participation and interest.
Any question? Or thank you, Aslan. Next presentation for the printing of shape memory polymer with the digital light processing and Tatsu.
değişmiyor.
Nasıl? Ama ilerlemiyor.
Tamam şöyle yapsak. Hani işte büyük ekranda değil de böyle mesela belki öyle düzelir.
Niye o kadar ekran değişmiyor lan anlamadım. Oraya bak ekran değişmiyor.
Hepsini kapatıp yeniden açalım isterseniz. Ama ayrıldı. Evet, onu kapatmak lazım.
Her başlatır mısın şu anda?
Belki onu başlat verelim.
Hazır vermiyor direkt. Niye vermiyor?
Çok heyecanlıyım.
4D printing is a novel technology that combines 3D printing with smart materials that can change shape or properties over time in response to external stimuli, has opened new possibilities for creating dynamic structures in many fields, such as aerospace, manufacturing, soft robotics, engineering, health, and also textile industry. And as you can see the figure 1, 4D printing is a function of 3D printing and the time as the fourth dimension. The 4D printing has produced the transformation of the printed 3D structure into a new and more complex shape under the environmental stimulus, like, as you can see here, thermal, light, hydro and humidity, pH, voltage, and also magnetic field. And also you can see the differences between the 3D printing and 4D printing as the figure 2. In the 3D printing, using the conventional materials such as polymers, ceramics, and metals to get a static structure, but 4D printing, using the smart materials such as hydrogels, bioinks, and shape memory polymers to get a dynamic structure with a stimulus by thermal light and hydro supported by the external stimuli to get a dynamic structure. And here is another application of 4D printing. This 3D printed part cannot cross across this physical or chemical barrier because of its so small size. And thanks to the 4D printing, this obstacle is eliminated as the rigid model with a tinier design reaches a larger size with its stimulating effect, and we can get a 3D printing part. As for the shape memory polymers are one of the smart materials that can be used for 4D printing. In the figure 4, you can see the shape memory cycle. This cycle has two hot stages, as you can see the red background, and two cold stages. You can see the blue background. Firstly, the original shape is straight shape, heated above the glass transition temperature, and then this shape forced into a special shape, pentagonal. This shape can be fixed after cooling, and this stage is called programming process, and the temporary shape is called programming shape. When this programming shape heated again, the glass transition temperature, it will return its original shape, and this stage is called recovery processes. And then we also using this research in digital light processing, and digital light process is a 3D printing technology to use the rapidly produced photopolymer parts. A DLP machine uses a projected light source to cure and entire the layer at once. The part is formed layer by layer, as you can see the figure 5. DLP is popular because of the high print speeds, total accuracy is sacrificed in the processes. And table 1, you can see the photopolymer resins printing parameters. And all of these parameters, the very important two parameters in here, one of them is bottom layer and the other layer exposure times, because those are we can achieve high print quality, dimensional accuracy, and surface roughness. To determine our photopolymer resins glass transition temperature, we use the differential scanner colorimetry analysis, and this analysis results glass transition temperature found nearly 110 centigrade degrees. And the shape memory test, as you can see the figure 7, bending test was used to determine the shape memory properties of the polymer samples. But firstly, I'd like to say something about the shape fixity ratio and shape recovery ratio. There are two important parameters in determining shape memory properties. One of them is shape recovery ratio, which is defined as the capability of the SMPs to regain its initial shape. And the other is shape fixity ratio, is meaning have the ability to maintaining the temporary shape after the removal of stimulus. And in this study, we use the external force for the stimulus. And also these ratios calculated by the following formulas, as you can see here. Then I say something about the bending test. Bending test, we use the different sizes samples, and one of them 30 millimeter, 10 millimeter, and 0.1 millimeter, and the other is 30 millimeter, 10 millimeter, and 0.35 millimeter. Both of the different thickness of samples were heated above the glass transition temperature, nearly about 120 centigrade degrees, as you can see here. Then try to fix it to fit a 10 millimeter thickness of mold by applying an external force here. Then after cooling in cold water nearly by 15 centigrade degrees, the maximum bending angle recorded was the theta max. Is here. The sample was shaped based on the mold by external force applied along 10 seconds. Then external forces were removed, and the temporary shape sample hold on the room temperature until it was fully dry and fixed. The sample with temporary shape memory expands by stretching a little, as you can see here. Then the angle at which this expansion is measured is theta fixed. In the last stage, we gradually heat the temporary shape from 95 centigrade degrees to 120 centigrade degrees. We recorded the bending angle theta t of the samples when they reached the glass transition temperature. And the results of the bending test is here. The temporarily shaped sample and the mold with the width of 0.35 millimeter are shown in the figure 8. As you can see, the mold and sample here. Then figure 9, B and D show the recycling processes of samples with thickness of 0.1 millimeter and 0.35 millimeter. It has been understood that 0.35 millimeter thicknesses of sample is more successful in recycling and shows an almost perfect results. As you can see, the D. And also, as for the temporary form in the figure 9A and C, the results were found to be relatively close to each other. And these graphics show us recovery ratio and fixity ratio data resulting from thermal analysis are shown in this section. The RF, it means recovery ratio and shape fixity ratio values obtained by performing analysis on 3 samples. For each thicknesses are given in the tabular form in the tables 2, 3, 4, and 5. In the table 1 and 2 and 3 show us the thicknesses of 0.1 samples. RF value is 9.74 and RR value nearly by 18.3. And the other tables show the thicknesses of 0.35 millimeter samples. RF value is found at 95 and the RR value is found at 92. According to the shape memory test results, shape fixity and shape recovery rates for the polymer resin vary depending on the sample thickness. Among these samples, the material with the highest average shape stability rate of 95% was determined to be the thickness of 0.35 millimeter samples. And similarly, the sample with the highest average shape memory ratio, 92% of was determined to the 0.35 millimeter thickness. And as a result, it has been revealed that the use of thickness of 0.35 millimeter polymer sample with the shape stability and shape memory rate of over 90% is more efficient with higher recovery ratio and shape fixity ratios in the production of the shape memory parts. And in addition, it has been understood that the digital light processing, one of the additive manufacturing methods, is extremely suitable for the 4D printing application due to its high surface quality and the time saving. As a consequence, it is thought that this study may be a guide for the development of shape memory polymer materials manufacturing with DLP and also for the printing application in such areas, technology, robotics, medicine, and biomedical industry. And thank you for the listening.
I have a question for notation. You write scientific notation is important.
Hocam açamıyorum ama.
Bu şeyden büyütürsen olur. Kapatmak için o. Bunun halinde F5, F5 ile verirsen bu ekrana gelir.
Tamam.
Ekranı karıştırırsın. And scientific notation is important. Sometimes this point, this is over, and use the two value, but sometimes use the three value. This,
Yes.
this omitting this value is result and use the zero, this, same scientific value. Thank you. Yes.
Thank you for your presentation. I want to confirm if I get the idea. You mean by 4D dimension that the object change their shape with the polygon and get the increased temperature. And you study this condition.
Tam anlamadım. I could not understand, but
For dimension is different parameter. Use the shape memory, use the temperature, change the temperature. This is one dimension. You product this material to three dimension. Another condition, yes, different.
The object change the shape.
Yes.
And her studies, she studies, for example, these conditions. For example, temperatures that
Evet.
what do you study? You study the conditions or the air?
For the printing, firstly you get this 3D printed DLP, this shape, but static. Okay, you get this static, but then you heat above the glass transition temperature this model, and so it can be rubbery form. Then you apply the external force, then its shape temporary form here. This is the 4D dimension. Then you can heat this temporary shape again, the heat glass transition temperature, it will be returned this one.
On this condition.
Yes.
Thank you. Thank you very much for the presentation, Professor. And next presentation, a case study on ultrasonic ionization on the stainless steel powder for the additive manufacturing. Emerald Oğlu.
Hello, everyone. Ekran paylaşımı yapayım.
Bir paylaşım yapacağız abi. Ekranı paylaştığım zaman
Can you see my screen?
No, we can't.
Now I think must be seen.
Now we can see. Yeah.
Or
Whatever.
Ekran paylaşımını yap. Güzel tamam.
Okay, then I start presentation.
1 second, please.
Okay.
Bir şey değişmiyor.
Tamam.
Orayı
görüntüyü paylaşmıyor mu? Biri ben anlamadım.
Ben de o ekranı.
Hı hı. Bazı orada kaldı.
Tamam. Niye mi söylemiştim?
Hı hı. İkinci ekran olarak orada karşı.
Nasıl ya?
Evet.
Başlıyor muyum?
Gerek olmuyor. Gerek olmuyor.
Diğer ekrana giderken.
İki ekran şeklinde
Ekran
görüyoruz.
olarak veriyorsun. Benimki ikinci ekran olarak algılıyor.
Bundan aldım.
Bundan olmuyor.
Hı. Ama buradan kontrol edeyim.
Duyamadım ama başlayayım mı? Şey,
Hocam biz
Bir uğraşıyoruz.
tamam, bekliyorum.
Nasıl yapayım?
Oraya gitmiyor ki.
Hayır, mouse.
Hocam Zoom'un ekranını oraya vermemiz lazım. Yaptık olmuyor. Bak olmuyor.
Ya,
Buraya vermiyor.
aslında şu an gelmesi lazım da projeksiyonla alakalı bir problem var. Yani. Bu klavye niçin çalışmıyor? Bir daha yetkili birini çağırayım. Onunla alakası yok. Burada açık ama
Burada
oraya
gidiyor.
veremiyorum şu an. Az önce sunumdan kaynaklıydı. O düzeltildi de buradan yapamıyorum. Çünkü ekran çift ekranlı. Tabii.
Bilmiyorum.
Yine de.
Neyle?
Tamam.
Hı,
Yine de. Evet.
tamam. Tamam. Tamam hocam, hallettik. Siz başlayabilirsiniz.
Okay. Hello everyone. Before we start, I want to introduce myself. I am Anıl Emrelioğlu. I have been working as a researcher at Gazi University Additive Manufacturing Technologies Application and Research Center, ECTAM, for more than 5 years. First of all, I would like to thank all the participants and guests. Our presentation will be about ultrasonic atomization, which is a relatively new topic in the field of powder production. We studied with my thesis advisor, Professor Dr. Rahmi Ünal, from Gazi University's Mechanical Engineering Department. The title of our research is a case study on ultrasonic atomization of stainless steel powder for additive manufacturing. I'm sure many of you have information about ultrasonic atomization, but I would still like to discuss its working principle. But before we start, on the left, you see the Atolab Plus ultrasonic atomization machine that we used in this study and owned by ECTAM. The other figure is a picture of the atomization chamber, inside of the atomization chamber. As you can see, we have three main components in the atomization chamber. These are the manipulator that moves the torch, the atomization platform through which the ultrasonic frequency is transmitted, and the wire feeding tip. Establishing an arc between the torch and the sonotrode is the first step to initiate atomization. Then the ultrasonic system is activated and wire feeding begins. Since it's exposed to a temperature well above its melting temperature, the wire melts and a melt pool forms on the atomization platform. Thanks to ultrasonic vibrations, the molten metal is separated into droplets, and finally these droplets are pushed into the chamber from the atomization platform with argon gas, and they quickly solidify and accumulate in the powder chamber at the bottom of the atomization chamber. What are the parameters? You see the parameters that may impact the properties of the powder to be produced. The ultrasonic frequency parameter directly affects the powder size, which is currently fixed and used at 20 kilohertz in this study. We will study the amplitude value in the later parts of the research, not in this paper. In this paper, we examined the effect of electric current, and it's not possible to keep the feeding rate constant throughout the entire process due to the characteristic features of the process. That's why we have question marks about including it in the research. And wire or rod diameter and torch angle will be added to the study in the future. And powder quality, of course, there are some criteria to determine the powder quality to be used in additive manufacturing machines. Having a narrow width of particle size distribution is essential for the repeatability of the process. The high sphericity of the powders ensures the proper formation of layers in powder bed systems. And there are two more factors that we will include in our research: oxygen level and chemical composition. Oxygen level is one of the most critical factors, of course. It's causing porosity in parts, and the differences in the chemical composition of the feedstock material and the powder are desired to be as small as possible. Moving on the materials and method. First of all, we use stainless steel 316L in our study. The chemical composition of the raw material is shown in the table on the left. And our feedstock material was a wire, and it has 1.2 millimeter diameter. We made 3 different productions by changing the electric current, since we used 120 ampere, 140 ampere, and 160 ampere current in these productions. So we named the powders as in the table. In addition to powders we produced, we also analyzed a powder we purchased that was produced using the vacuum induction gas atomization method. We used the Atolab Plus machine that I mentioned before for the production of powders, and microtrack zinc analyzer for particle size distribution and sphericity. And we also used the Zeiss X-Radia Versa micro CT machine to analyze sphericity images, satellite analysis, and gas porosities. This is the particle size distribution results. When we look at the table, we see that the powders produced by ultrasonic atomization methods are smaller than powder Vega. However, since our primary motivation here is the particle size distribution range, so we analyzed it. Considering the span ratios, we can easily say that all the powders used meet the criteria. It must be less than 1.5, and its formula is shown in here. In the case of powders produced by ultrasonic atomization, it's observed that the D10 and D50 values of the powder 160 are less than other powders. There was little difference in the 90 values. When sphericity ratios are examined, there is a dramatic difference, really dramatic difference between gas atomization and ultrasonic atomization methods. While the rate of powders produced by ultrasonic atomization has a sphericity higher than 98%, varying between 58 and 87. And this rate is only 2% in powder Vega. Although it's seen that the powders produced with high electric current are less spherical at high sphericity values. But the graph doesn't have a distribution that we can generalize in ultrasonic atomized powders. And you can see two figure in here. The powder you see on the left is the CT image of powder 140 powder and produced by ultrasonic atomization. And there's no satellite or gas porosity was found in this powder. As you can see, many porosities and satellites in the powder Vega are produced by the gas atomization method on the right. Additionally, the difference between the sphericities of the particles is also noticeable. And the conclusion, 316L powders produced by the UA method, ultrasonic atomization method, are dramatically better in terms of sphericity. And when comparing micro CT images, the powders produced with UA showed almost no porosity and satellite formation. At the same time, these problems were observed in the Vega method. The particle size distribution of the powders produced with UA is narrower than Vega, but this difference is not significant enough to be considered. Increasing the electric current in powder production with ultrasonic atomization does not significantly change at low currents, but when currents can be considered high, such as 160 amperes, deterioration in the sphericity of the particles may occur. In addition, the proportion of the particles smaller than expected increases, and the UA method has advantages in producing more spherical and denser powder compared to the conventional methods. However, it has a slower production rate than conventional methods. Therefore, its commercial use is limited. Maybe with innovations and expansion of the material spectrum, it will be used more widely in the future. This study is supported by TÜBİTAK 1004 program, and the used powder in this study was produced and supplied from ECDAM. Thank you for them, and thank you for you. Yes.
Thank you, Emre Alevoli. You have a question? Presentation. Thank you for presentation.
Okay.
Next presentation is an application again temperature and magnetic noise and adjustable constant current DC that drive under the 15 volts.
Hello everyone, I am Mehmet Bingir. I am electronic engineer from Xenophysics Technology. I am hardware design engineer and I am master scientist students at Konya Technical University electronic engineering department. Our presentation is design application against temperature and magnetic noise in adjustable constant current DC LED drivers under 50 volts. This study focuses on changing the design of DMX 512 based LED drivers for professional lighting. It addresses changes like heating and magnetic noise, especially at high currents. By referring to circuit topology, component selection, and PCB design, the research aims to improve to performance and lifespan of small size LED driver in demanding application. Instruction and background. LED drivers are essential for energy efficiency and longevity in professional lighting. The DMX 512 protocol allows precise control over digital signals. PWM-based LED drivers offer efficient brightness, color, and intensity control, making them popular in various lighting applications. This study aims to design stable DMX 512 compatible LED driver and unchanged performance by reducing heating and magnetic noise. Literature review. Existing research highest the need for improvement in DMX 512 and PWM-based LED drivers, particularly in energy efficiency, electromagnetic compatibility, thermal management, and intelligent control. Patents suggest innovative solutions like integrated devices, adaptive colors control, and wireless DMX PWM, a common modulation method in LED drivers. Adjust LED brightness by varying the path width of the applied voltage or current. Different control methods offer advantage in brightness control, energy efficiency, and EMI reduction. Hardware design. This study uses a microchip constant current LED driver, MySemix DMX 512 receivers, and decoders. Texas Instruments MOSFET and other components. The microchip drivers offers plus or minus 3% output LED current accuracy and operates from 8 volt to 412 volt supply. The MySemi decoder supports standard for DMX 512 protocol and provides for open drain output. The Texas Instruments MOSFET is 5.7 million 60 volt MOSFET designed for industrial buck converter solution. CACAT and electronic load device were used for design and testing. PCB design. The electromagnetic interference caused by high frequency PWM signals and high current. If you have a high current signal, high current and high frequency signal, you must produce electromagnetic noise. Cooling problems due to increased component placement and high current. Insufficient grounding, a factor contributing to observed issues. Solution includes efficient converters, EMI filtering, thermal management, and circuit optimization. This PCB is nearly 203 millimeter long and 30 millimeter width, optimized for standard wall washer. high currents cause heating and magnetic noise attributed to electromagnetic interference. Cooling problems and insufficient grounding solution include efficient power converters, effective EMI filtering, proper component placement, heat dissipation, cooling techniques, and circuit optimization. I want to use this image for presented radiated emission. Radiated emission is electromagnetic energy emitted through the air during operation and electronic device or systems. This typical emission occurs due to electromagnetic fields created around circuits and components inside the device. Radiated emission is usually measured the frequency range from 30 megahertz to several gigahertz. These emissions can cause unwanted interference, especially to radio frequency device and communication systems, and therefore must be limited under certain regulation and standards. This is our conducted emission test setup. Conducted emission test setup followed CSPR 1621 standards using TechBox TBLC 08 listen and Regal spectrum analyzer, and other test setup is radiation emission test. Normally radiated emission test must be used in a parallel case, but in laboratory we make like this. Radiated emission test used near field probes and amplifier for amplify signal, and a Regal spectrum analyzer. Thermal test employed for unit UETL 80 to 12 plus load with a maximum PWM signals to measure MOSFET and coil temperature. Result and discussion test at 24 volt DC and various current level. Relevant and nonlinear temperature increase with rising current, magnetic noise peak and frequency remained relatively stable up to 750 milliamp, but increased at 1100 milliamp. The conducted emission noise also increased non-linearly, especially at higher currents. To study implemented thermal protection mechanism, thermal vias, copper pads, parallel capacitors for EMI mitigation, and DMX512 signal lines. Constellation and feature works. This study demonstrated that optimizing component selection and circuit design significantly reduced thermal and magnetic issues in DMX512 changeable current LED drivers. The adjustable current range ensures high LED driver performance and lifespan. Addressing cooling and EMI problems with appropriate component provides a reliable and efficient solution for professional lighting project. Future research could explore advanced thermal management techniques and further optimizing circuit and even greater efficiency and noise reduction. Different optimization algorithm can be tested by creating a system model. Thanks for your attention.
Thank you, presentation Gökçe. You have a question? No? I have a question.
Okay.
You testing megahertz up to the several gigahertz, but only use only one 16 megahertz about only test.
We have make two tests. One is the conducted emission, one is the radiated emission. Conducted emission test starts with 9 kilohertz to 30 megahertz. But radiated emission test started at 30 megahertz, and we finished at 1 gigahertz, but it can tested upper frequency.
Thank you. Thank you
Welcome.
for the presentation. Thanks. Another next presentation, investigation of the structural, mechanical, electronic, and optic properties of cubic percoise potassium using the first principle methods, the G çorbacı. Thank you.
Paylaşacağım.
Good afternoon, I am Gülçin Çorbacı. I am graduate bachelor student in physics department at Gazi University. Our study name is Investigation of Structural, Electronic, and Optical Properties of Potassium Silicium iod-3 cubic perovskite using first principle methods. At the beginning, here is our contents, and those are our main subjects that we will discuss about. At first, we will start purpose, and then it continues introduction. And then theoretical background, and then we will show you some physical investigations of our studied materials, such as structure, electronic, and mechanical properties. This study aims to understand and analyze the metallic cubic potassium silicium iod-3 compounds' fundamental physical properties using first principle methods. A better understanding of the material's properties enables understanding of the material's properties enables us to learn about the potential impacts of this study on experimental and theoretical applications. This study investigated structural, elastic, electronic, and optical properties using the WEST program. The results obtained showed that the compound we examined was mechanically stable. Analyzing the investigated properties and filling the gaps in the literature, it aimed to lead experimental studies and form the basis for future studies in this field, non-toxic perovskites. The ABX3 perovskite family, comprising a broad spectrum of ternary oxides, present significant potential as a functional material for diverse applications. These applications extend across chemical engineering, thermal engines, hydrogen separation membranes, actuators, sensors, electrochemical systems, and solid oxide fuel cells. Despite expensive research on the structural, elastic, dielectric, and piezoelectric properties of pristine ABX3 perovskites and their alloys, further investigation is required to fully harness their potential. The tunable piezoelectric and dielectric responses observed in perovskite solid solution make them particularly suitable for various technological advancements, including high dielectric constant capacitors, ferroelectric thin film memory devices, and like this. Previous studies have shown that perovskites exhibit both semiconducting and insulating properties. A better and more fundamental understanding of their semiconducting properties is necessary to evaluate and improve specific devices. However, most of the existing perovskite complexes contain toxic lead, which is an undesirable situation. This study was conducted to investigate the structural, electrical, elastic, and optical aspects of the silicium-based metal perovskite potassium silicium ion-3, which we used DFT method. DFT is a quantum mechanical computational method used to investigate the electronic structure of multi-electron systems. Instead of directly solving the Schrödinger equation, DFT calculates the system's energy and other properties based on the ground state electron density. As a result, various approximations have been developed within the DFT framework, with the local density approximation, its LDA, and generalized gradient approximation, its GGA, being the most commonly used. All computational tasks in this study were performed using the Vienna Ignatius simulation package, its VASP. The Purder-Zunger type generalized gradient approximation function was employed to model exchange correlation effects within the electron-electron interactions. A plane wave-based set with the kinetic energy cutoff of 7050 electron volt was utilized within the projector augmented wave, its POW method, to describe electron-ion interactions. A 14 Moncourse pack cowpoint mesh was adapted to sample the Brillouin zone, and elastic constants were determined through a stress-strain analysis. So I will give information about the structural and elastic properties. Elastic properties are a calculation we use to test the stability of the material. When we look at the table 1, we can see the elastic properties of our materials. The elastic constant C44 is important to us in here because the C44 indicates to us the hardness of the material. And Poisson and Park ratio is about the ductility and brittleness of the material. If Park ratio is smaller than 1.75, that indicates the material is more brittle. So when I look at the table 1, our material is brittle, as you can see. I like to show the electronic properties for our materials. When I look at the figure 2, I can say that our material is metallic because the valence band and transmission band is coincide. There is material similar to our study in the literature, but our study is not in the literature. And when total and partial density of states graphs are examined, it's observed that they are in agreement with the band structure. In the valence band, the contribution from the K-P band is dominant in the low energy range between -15 and -10 electron volt. There is also a contribution from the S band of the I atom. In the conduction band, contributions come from the P and D bands of K and C atoms. There is a small contribution from the D band of the I atom as well. The maximum peaks formed in the valence band near the Fermi energy are suitable for ferroelectric materials. This site indicates to give the contribution to valence band and this side to conduction band. So optical properties is important for us in here. Optical properties describe the interaction of a material with electromagnetic waves and are commonly characterized by parameters such as the dielectric function, refractive index, and absorption coefficient. According to figure 4, the real part of the dielectric function is epsilon 1, has a static value of 34.9 and a peak value of 7.78 at 4.1 electron volt. And imagine the electric constant, its epsilon 2 is related to interband transition, which can reflect how much electron transition a material undergoes. As can be seen from figure 5, epsilon 2 starts to increase rapidly around 3.8 electron volt, which can be attributed to the electron transition between the IP state at valence band maximum and the silicium P state at conduction band minimum, which is also consistent with the result observed in the PDOS graph. The maximum peak is in the visible region between 1 and 3.5 electron volt. Since this is a metallic, there is no optical band gap. We can see this from the fact that imagine part starts from 0. The M value is 5.9. The refractive index indicates how much light slows down and changes direction when passing through a material. Materials with a high refractive index are preferred for devices such as lenses and optical fibers. Relatively large refractive index values are attributed to the small band gap of materials. A small band gap increases the electronic polarizability of the material, leading to higher refractive index. The highest peaks of the refractive index are in the UV region. It has a minimum value around 12 electron volt. The extinction coefficient is in figure 7, measures how much an electromagnetic wave weakens as it propagates through a material, and it's directly related to the absorption of radiation. The energy-dependent behavior of K is similar to that of the imaginary part of the dielectric function. The maximum peak is obtained around 1 electron volt. And here is our results, optical results. The absorption coefficient provides information about the material's ability to convert solar energy and indicates how deep light of a specific frequency can penetrate into the material before being absorbed. Alpha can be used to assess the material's sensitivity to sunlight, showing how the photons are captured in the relevant light range, those affecting the generation of electron hole pairs. A more detailed analysis of the calculated absorption spectrum clearly shows that alpha increases continuously with increasing energy and reaches its first peak at approximately 4.2 electron volt, which corresponds to the electronic transition between the valence band maximum and the characteristic peak at approximately 4.2 electron volt in the dose diagram, indicating an excellent optical response to light in the UV region. Additionally, the optical absorption H of potassium silicium io3 appears at the band gap of approximately 4.2 electron volt and exhibits a higher absorption coefficient above the band gap, indicating an excellent optical response to light in the UV region, as I said. In summary, I need to say that we have obtained results. The alloy was modeled using DFT to obtain elastic, electrical, and optical properties. The calculated properties were compared with experimental results. The alloy showed a complex and challenging behavior under various conditions. And the results obtained suggest that certain criteria need to be improved. Further theoretical and experimental investigations are required to understand the behavior of the alloy in more detail. And thank you for listening.
Thank you very much. This is Çorbacı. You have a question? No? This first table, mechanical elastic properties, B and G ratio.
Ratio,
This
yes.
B value is 3 scientific number, but use the 4 number. This only omitting because the scientific notation is important. Okay, the ratio omit the 4, 5 is omitting is good result. Thank you for presentation.
Thank you.
Have a coffee break.
Neyi? Tabii ki. Bu. Neyse. Evet, şu da bende.
Teşekkür ederiz.
Teşekkür ederim.